In this lesson, we're looking at proof by induction and divisibility proofs. I thought it's probably easiest to go through an example. Now, the idea is that we're still doing the same three things. We're still trying to show that it's true for n equals 1. We want to assume it's true for n equals k, and then hopefully then we can prove it's true for n equals k plus 1. So there's a couple of slight differences, and there's an approach that we take that we need a little bit of practice. But we'll start going through the process. So the first thing we're going to do is show true for n equals 1. And so what we're trying to do is show that 7 to the power of n take 4 is equal to 3a for all values a which are elements of a set of natural numbers. If we can see that it's 3 times something, then we've shown that it's true for n equals 1. So left-hand equation, we have 7 to the power of 1 take 4, which is equal to 3, and we can write that as 3 times 1. So therefore it must be true to that right-hand equation, and it is true for n equals 1. Okay, so that's nice and easy. Assume true is a very straightforward step. Assume true for n equals k. So we've got 7 to the power of k, take 4 is equal to 3b for all values b which are elements of a set of natural numbers. And we want to use this then to prove true for n is equal to k plus 1. So what we're required to prove then is that 7 to the power of k plus 1 take 4 is equal to 3c for all values c which are elements of a set of natural numbers. Alright, so let's work with this left-hand equation. Left-hand equation gives us 7 to the power of k plus 1 take 4. Now, if we use our index laws here, we can see that this is 7 to the power of k multiplied by 7 to the power of 1 take 4. Now the trick is here that we want to be able to identify or create this 7 to the power of k take 4 so we can replace it with that 3b. So the trick is that we can say this is 7 to the power of k times 7, and we want to have a 7 by 4 there so we can take 7 out as a common factor. So 7 by 4 is now 28. So we've got 7 to the power of k take 7, take 28. We need it to be equivalent to the last line. So for it still to be negative 4, we need to have plus 24. So we've manipulated it, but we haven't changed it. Here we can say that common factor of 7 leaves us with 7 to the power of k take 4 plus 24. And now that we've isolated that 7 to the power of k take 4, we can substitute in 3b. So 7 times 3b plus 24. Now this last step is realizing that both of these terms have a factor of 3. So if we take out 3, we're left with 7b plus 8. And we can now say that this is equal to 3c, where c is equal to 7b plus 8. So since we've got it down to a point where we can show that divisibility, it's 3 times something, then it must be equal to that right-hand equation. And we've proven true what we were trying to prove, so QED. Once we've done that, we can say, therefore, as true for n equals 1, n equals k, and n equals k plus 1 must be true for all values n which are elements of a set of natural numbers. That's it. So that is divisibility proofs. You'll have to practice this little section here. The whole idea is that we try to set up so that 7 to the power of k take 4 is part of the expression. Of course, if we do that, we can always replace it with whatever it's equal to, in this case, 3b. So that's going to be our approach. That assume step is really important to get that statement there so we can perform that substitution later on, and we know what we're aiming to isolate within this expression. Okay, so that is proof by induction divisibility proofs. Still the same approach, still show, assume, and prove with a little bit of a twist.